Hi everyone, this is Mr. Bowman, and these are the second day of notes on section 2.1, which is about the derivative of a function. As you recall, on the first day we introduced the idea of the derivative, and we looked at a couple of formulas for finding that, couple different methods for doing that, did some examples, and then we talked about notation. And then we sketch some graphs of some derivatives based on the function. In this video, we are going to talk about what it means to say a function is differentiable and not differentiable. And we're going to go through an example of that. And then you are going to match some functions to their derivatives, and then a little bit more practice sketching derivatives from the function. So let's start with this idea of differentiable. A function is differentiable if it has a derivative on some interval. In other words, if it has a derivative at every point on some interval. So f of x is differentiable that simply means it has a derivative on some interval AB if it has a derivative at every point on the interval from A to B. So that's simply some terminology. So if we say f of x is differentiable on the interval AB, that means that every point on AB, the derivative of f of x exists. Now, there are some cases where a function is not differentiable, so I want to talk about that as well. A function is not differentiable at a point if its left hand and right hand derivatives are not equal at that point. So you have to remember that a derivative is a limit, and a limit exists if the left and right limits are equal to each other. So a function is not differentiable, aka or i.e. does not have a derivative at a point if its left and right hand derivatives are not equal to each other at that point. So what I'd like to do is I would like to illustrate by way of example a function that is not differentiable at a point. So f of x is the piecewise function defined as x squared when x is less than 1 and x when x is greater than or equal to 1. As you can see, the function transitions from the x squared function to the x function at x equal 1. So what we're going to do is we're going to look at a Desmos example of that. And in the upper right hand of the graph here, you can see the purple point on that piecewise function as at x equal 1. Left of that is the function x squared. To the right of that is the function x. And so what we see is we see that the slope to the left of x equal 1 appears to be different than the slope to the right. And they don't approach each other as x approaches 1 or as h approaches 1 in our derivative. So we're going to illustrate that with this Desmos example here. So our purple point is the point where we're trying to find the derivative. The green point is to the left of x equal 1 when h is negative. It is to the right of x equal 1 when h is positive. And we are going to draw in the secant line. And there's our secant line. And now we're going to experiment as we move h towards 0, but h is positive. So in other words, this is the right-hand derivative. If you see right here, about the middle of my screen on the left, it says that the slope, f of a plus h minus f of a over h, as h is getting very close to 0, but it's positive, the slope is equal to 1. Now we're going to move over to the other side where you can see that h is negative. So this is the left-hand derivative. The slope is currently 1.81, but as we move closer and closer to 0 for h, the slope appears to be approaching positive 2. So in other words, our left-hand derivative is positive 2 and our right-hand derivative is positive 1. They're not equal to each other, therefore the derivative does not exist for this piecewise function at x equal 1. Now, how do we do that algebraically? Here's how we do that algebraically. All right, so left-hand derivative at x equal 1, and then over here we're going to have the right-hand derivative at x equal 1. All right, so we set this up the same way we always do. The limit as h approaches 0, but it's going to approach 0 from the left. So h is actually going to be negative of f of x plus h minus f of x over h. So that's going to be the limit as h approaches 0 from the left of 1 plus h quantity squared minus 1 over h, because we're taking the derivative at x equal 1. That is going to be the limit as h approaches 0 from the left of 1 plus 2h plus h squared minus 1 all over h, which you can see the 1's cancel out, and this simplifies to the limit as h approaches 0 from the left of h times h plus, 2h plus h times 2 plus h, all divided by h. The h's cancel out, and the result is 2, what we saw on Desmos. Now we're going to do the same thing for the right-hand limit. So the limit as h approaches 0 from the positive direction. So h is still approaching 0, but h is positive, of f of x plus h minus f of x all over h. Well, the function that we are using is going to be the x function because h is positive. We're to the right of x equal 1, so it's going to be 1 plus h minus 1 all over h. which you can see simplifies to the limit as h approaches 0 from the positive direction of h divided by h, which is equal to 1. Therefore, the limit as h approaches 0 of f of x does not exist. The left and the right hand derivatives are not equal to each other. I want to reiterate, we have to be able to do the algebra. We just did the algebra, but we also have to remember what we're seeing here. What we're seeing is that the slope of the tangent line is 2 when we approach x equal 1 from the left. The slope of the tangent line is different, or 1 in our example, as we approach from the right. The left-hand derivative, i.e. the slope of the tangent line from the left of x, at x equal 1 is 2, and from the right is 1. So basically we can see that if we're zooming in on that graph there and taking a close look at that point, but we also have to be able to deal with that algebraically. So in the next part of this, I am going to have you pause the video, and I want you to match the 5 functions a through e on the left to their derivatives on the right. Remember, the derivatives are the slopes of the tangent lines. So pick an x value, estimate the slope, move to the right a little bit, estimate the slope, keep moving to the right, estimate the slope, and so on and so forth, and then try and match that with the function at the right. When you're finished, unpause the video and check your answers. So, graph 1 on the right is the derivative of function d. Graph 2 on the right is the derivative of function b. Graph 3 on the right is the derivative of function e. Graph 4 on the right is the derivative of function a, and graph 5 is the derivative of function c. If you didn't get those correct, take some time, think about it again, talk to the people around you, and see if you can understand why those graphs on the left match up with those derivatives or graphs of their derivatives on the right. On the next page, you're going to see 8 graphs. And what I'd like you to do with these is I would like you to draw the derivatives of their functions in the same viewing window. So we're going to do the first one together, then you're going to pause the video and draw the rest of them, and then when you're done, you're going to unpause the video and check your answers. So remember, derivatives are slopes. So what do we have here? When we start at the left on graph 1, function 1, the derivative is very negative. But the slope is increasing in value until it gets to 0. So I'm going to mark some key points there. The slope is 0. The derivative is 0 at that x value. Now the derivative becomes positive, and at x equals 0, the derivative, the slope of the tangent line, is 0 again. And now the derivative goes negative. And then at this x value right here, the slope of the tangent line is 0 again, and then it goes positive. So I hit some key points on there. Now I'm going to graph the derivative. The derivative is negative until it reaches this 0 value here. Then it goes positive, but it's starting to come back down. The slope is actually decreasing, and then the slope reaches 0. And then the slope goes negative for a while, but it starts to increase again because, even though it's negative, because it has to be 0 there. And then the slope gets, well, the tangent line gets really steep, so the slope becomes very positive. So go ahead and pause the video and try and graph the derivatives of each of these functions in the same viewing window. When you're done, Turn the video back on, check your answers. All right, so here are the answers in red. In red, you see a rough sketch of the derivatives of the given functions. Pause the video, take a look at those, and see which ones you got wrong. The ones that you got wrong, I want you to spend a few minutes talking to the people around you about why they are the way they are. Number 8 specifically shows a great example of a function that's not differentiable at x equals 0. It is the absolute value function, and as you know, the derivative from the left at x equals 0 is -1, and the derivative from the right is +1, and that's why the derivative is shown the way it is. But the function is not differentiable at x equals 0 because the left and the right derivatives are not equal. When you're done with all of this, you can stop the video and start working on your homework.